Hello everyone, I'm Chen Wang, currently a postdoc at Harvard University. Today I'm presenting our study, a survey on ML4VIS, applying machine learning advances to data visualization. When we say ML4VIS, we mean studies which employ the capabilities of ML to extract knowledge from data and use the knowledge to fulfill the needs in creating, designing, and evaluating visualizations. Recent years have witnessed an increasing number of ML4VIS studies. A structured understanding of the integration of ML and VIS is needed to promote and guide future studies. First, not all visualization problems are suitable to be solved by ML. Some problems might be too simple and do not need ML or have very fuzzy goals that cannot be mathematically defined. Blindly applying ML to those unsuitable visualization problems may only impose drawbacks without bringing any benefits. Second, even when we identify a suitable visualization problem, it can hardly be solved if we select an improper ML technique or fail to employ necessary adaptation. Therefore, we ask two primary questions in this survey. Where do the needs for ML exist in visualization? And how can the capabilities of ML be used to satisfy those needs? Driven by those two primary questions, we reviewed recent literature, summarized the current practice, and discussed future directions. The result of this survey is available as an online interactive browser, ML4VIS.github.io. You are more than welcome to contribute to it by adding new ML4VIS studies. Now, let's take a look at our findings and insights from this survey. The first question we try to answer is, where do the needs for ML exist in visualization? The visualization process is not a new topic and has been well studied in our field. For example, the pipeline proposed by Card describes the computational process of converting information into a visualization. In the venue of visualization, when Venjica proposed a visualization model for the processes and the context in which visualization operates. Based on those existing visualization pipelines and models, we identify 7 ML4VIS processes where visualization problems can benefit from the employment of ML techniques. We further group the 7 processes into 3 main containers: data, visualization, and user. I will not introduce each process due to the time limitation. Please refer to our paper for more details. Note that the 7 processes are not isolated from each other but connected. The output of one process can be used as the input of another process. Therefore, employing ML technique in one visualization process can further facilitate other processes, even though ML techniques are not used in those processes. Let's take our previous study as an example to show the relationship between two ML4VIS processes, with reading and style imitation. Here, the users want to create infographics that have similar styles to the example images. At the first glance, this is a problem of style imitation. However, directly generating a visualization image is not an easy ML task. The ML models are usually hard to train or have inferior image quality. Therefore, we convert the visualization problem into a VIS reading problem. Instead of directly generating visualization images, we extract a template from the image and use such a template to create visualizations for new data. Such a conversion enables us to solve the problem using more mature ML techniques, such as object detection and instance segmentation. In this diagram, the link indicates the collections that we have identified in the surveyed papers. Meanwhile, there are many unconnected processes that may illustrate promising directions. For example, the user characteristic extracted from the user actions can be used to create customized visualizations that better consider individual users' needs, abilities, and performance. Once understanding the needs for ML in visualization, the next question is how can the capabilities of ML be used to satisfy those needs? We categorize the existing ML4VIS studies based on the type of ML tasks: supervised, unsupervised, semi-supervised, and reinforcements. To be formed as a supervised learning task, a visualization problem needs to have a training dataset. Many visualization dataset has thus been proposed, covering a diverse set of visualization problems. To enable those datasets, a visualization problem needs to be described using either numerical or categorical values. For example, numerical values can describe the position of graphic elements or the importance of each pixel in a visualization image, solving problems in a VIS reading process. However, not all visualization problems can be solved by providing numbers. For example, it can be hard for humans to assign one exact number to describe the quality of a visualization. A classification label can describe the type of user actions, the type of visualization charts. Some complicated problem can be decomposed into a set of classification problems. For example, VisML recommends a visualization through a set of encoding level and visualization level classifications. However, for more diverse and customized visualizations, such as infographics, describing all possible outputs as a finite number of classes can be very challenging and requires a comprehensive understanding of the design space. To be formed as an unsupervised learning task, a visualization problem needs to be solved by finding or generating samples based on the distribution of training data. For example, in the tempo visualization of density maps, unsupervised learning can generate visualizations for the missing time points by learning the tempo distribution. In semi-supervised learning, a model is trained using a small amount of labeled data with a large amount of unlabeled data. An interactive mechanism should be provided to actively query new labels from the users. And lastly, for reinforcement learning, the solution of a visualization problem should be formed as a set of actions, and the quality of the solution should be represented by the rewards of actions. For example, in style imitation, creating a storyline can be decomposed as a set of actions, and the rewards can be represented as the similarity between the current layouts and the ground truth layouts. Now, let's see some statistics about the current practice in ML4VIS. In this chart, each column indicates an ML task and each row indicates a visualization process. The cell indicates the number of papers for the corresponding visualization process and ML tasks. We can see that supervised learning is the most widely studied ML technique, which is not surprising and consistent with the practice in other domains. Reinforcement learning and semi-supervised learning are relatively less used, calling for more diverse ML techniques and more close human-AI collaboration. In terms of the visualization process, data with mapping and with reading are the two most frequently studied processes. The large number of studies in with reading might be related to the great success of ML in computer vision tasks. Despite the wide popularity of the two visualization processes, some directions are still underexplored. For instance, current ML4VIS studies mainly focus on single view and standard visualizations. Multi-view visualizations, visualization interactions, and animations are relatively less investigated. Also, the adoption of ML techniques for visualization data is still missing. Here is an example demonstrating the difference between nature images and visualization images. For nature images, small changes typically have little impact on its interpretation. On the contrary, visualization images usually convert information using sparse visual elements. Even small changes can completely alter the meaning of a visualization. In summary, in this survey, we identified 7 visualization processes that can benefit from the employment of ML techniques. We summarize how to form different visualization problems into 4 main types of ML tasks, and discuss current practice and promising directions. At last, a small advertisement for myself. I'm on the job market and looking for a faculty or research position starting from 2023. Thanks so much. Your questions and comments are welcome.